Welcome students. This is the second lecture on gas turbine. In the first lecture, you have learned the what is gas turbine, the different type of gas turbines and its application in different areas, different industrial areas, the comparison of different type of gas turbine, and also we have derived the efficiency in case of Breton cycle. So now we are going to start. The Now we are going to learn about the different efficiencies of other gas turbine cycles, such as heat exchanger cycle, reheat cycle, intercooler cycle, etc., etc. So let's start. So as you can see, this is the heat exchanger cycle. So in this figure, this is the compressor. This one is the compressor. This one is the turbine, and this is the combustion chamber, and these three are common, same as the Breton cycle, and this one is the heat exchanger. Okay, let's see what happened. So first, the the compressor sucks the air into it. This is the process 1 to 2. This is 1 to 2. This is the adiabatic compression process. This is the adiabatic compression process 1 to 2. After being compressed, the air flows into the heat exchanger. Heat exchanger is the 2 to 5. In this picture you can see this is the 2 to 5. This is the 2 to 5 process. So in the heat exchanger, what happened, it's exchange heats, or the compressed air gain heat from the flue gas. In the heat exchanger, the compressed air uh, gain heats from the flue gas. Okay, then the compressed air flows to the combustion chamber. This is 5 to 3 process. This is 5 to 3. So 2 to 5 and 5 to 3, this total process is a constant pressure process. Okay, in this TH diagram you can see this is 2 to 5 and 5 to 3. In the 2 to 5, the compressed air gain the heat from the flue gas, and 5 to 3 is the combustion chamber process. In this process, this 5 to 3 process, the fuel is added here and the combustion takes place in 5 to 3. Okay, then this combustion product then flows through the turbine, that means 3 to 4. This 3 to 4, this is the adiabatic expansion process. Adiabatic expansion process 3 to 4. But here you, in the TS diagram, you can see 3 to 4 is the constant entropy process. Okay, then after flowing through the turbine, the flue gas is flows to the heat exchanger, flows into the heat exchanger. Then it exchange heat with the compressed air, as I have told you earlier. So that flue gas uh, loses some heat, and it being folded, and the compressed air that comes from the compressor, it's gain heat. Okay, this process is 4 to 6. Here 4 to 6. Okay, it's the constant pressure process 4 to 6. The flue gas lose here heat, and the 6 to 1 process, this is the 6 to 1. The 6 to 1 is the exhaust. Okay, so let's derive the efficiency. So the heat addition process is 5 to 3, is a combustion chamber process 5 to 3. So that is the enthalpy difference H3 minus H5. Okay, H3 is the higher enthalpy and H5 is the lower enthalpy, the cold air enthalpy. So that is equals to Cp into T3 minus T5. T3 is the higher temperature and T5 is the lower temperature. Now the specific work output formula is Wn by Cp into T1. Wn into Cp into T1. So one second. This is the Breton cycle process. One thing that I am going to remind you, that is Wn is equals to nothing but Wt minus Wc, the turbine work minus the compressor work, and the specific work output, that is Wn equals to Cp. Uh, this is the net work done. Net work output is equals to Wn equals to Cp into T1 into T3 by T1 minus T4 by T1 minus T2 by T1 plus 1. Okay. So the specific work output is Wn by Cpt1. So specific work output becomes Wn by Cpt1. So this is the specific work output formula, W by Cp into T1. This formula is same as this Breton cycle formula is same as the heat exchanger cycle formula, same as with the heat exchanger cycle formula. And another thing, that is small t is nothing but the ratio of higher temperature to lower temperature, that is T3 by T1. T3 is the higher temperature and T1 is the lower temperature. So small t is the ratio between the higher temperature to lower temperature, and r, small r, is the pressure ratio, that is P2 by P1. This is P1, this line is P1 and this line is P2. So higher pressure by lower pressure is the pressure ratio, and C is nothing but R to the power gamma minus 1 by gamma. Okay. So in the heat exchange cycle, the specific work output is same, that is Wn by Cpt1, that is equals to T into 1 minus 1 by C minus C minus 1. Okay. And the net efficiency becomes net work output, that means Wt minus Wc, turbine work minus compressor work, by Q. Q is the heat input. So heat input is this. Okay. So the efficiency becomes 1 minus C by T. Okay. Now we can say that as the efficiency increases in T, that is it is depends upon the maximum cycle temperature. As efficiency increases with pressure ratio, with decrease in pressure ratio. Okay. Efficiency increases with decrease in pressure ratio. And this is the reheat cycle. Okay. In the reheat cycle, as you can see in the diagram, is the reheat cycle arrangement diagram. This one is the compressor, this is the combustion chamber, this is the turbine, first turbine, then again this is the reheat combustion chamber, and this one is the second turbine. Okay. So let's see the working principle of the reheat cycle. First, the air is sucked in the compressor, then it's first the air is sucked in the compressor, that is the process 1 to 2. I mean, the air is then flows through the compressor, that is the adiabatic compression process, that is 1 to 2, that is given, that is shown in the PV diagram, that is 1 to 2 process. This is the 1 and this one is the 2. So is the constant entropy process. So that little bit of temperature is increased here. Then that compressed air then flows to the combustion chamber. This is the first combustion chamber. Then fuel is added and combustion takes place. Then the combustion product is flows through the turbine, that is 3 to 4. This is the expansion process. This is the 3 and this point is the 4. Okay. Is 3 to 4. The temperature is decreases. It's a constant entropy process, the adiabatic process, actually 3 to 4. Then that product again it flows to the it flows to the reheat combustion chamber. In the reheat combustion chamber, this is the reheat combustion chamber. It's again mixed with some fuel, and again the combustion takes place, that is 4 to 5. This is 4 to 5. So the 4 to 5, again the temperature is getting increased at point. This is the process 4 to 5. Okay, this is a constant pressure process. Then 5 to 6 is the uh, then the combustion product, then again the flows through the turbine, that is 5 to 6 is the adiabatic expansion process. This is the 5 to 6. This is the 5 to 6 or constant entropy process. Okay, so and 6 to 1 is the exhaust. Okay, simply the exhaust process. So let's see the how to derive the efficiency of a reheat cycle. So first of all, in the reheat cycle, the heat addition takes place in two ways, that is 2 to 3. The in the first combustion chamber, this is 2 to 3, that is H3 minus H2. So the value is Cp into T3 minus T2. And the second heat input process is 4 to 5, that is H5 minus H4. This is the second heat input chamber, combustion chamber, that is Cp into T5 minus T4. And the turbine, since there is two turbine is present, so we can write W T3 W 3 to 4, that is H3 minus H4, or Cp into T3 minus T4, that is T3 minus T4. This is the turbine process, expansion process. And again W 5 to 6 or H5 minus H6, that is Cp T5 minus T6. This is the 5 to 6, the second turbine expansion process. Okay. So another thing that we are going to assume that the pressure ratio, that means the maximum pressure ratio, that is R, is that we have seen earlier. R is the maximum pressure P2 by P1. Okay, this is R is nothing but the ratio between the P2 by, this is suppose this is P1. So R is the ratio between P2 by P1. So that is equals to R3 into R4. R3 into R4. So now what is R3 and what is R4? So the R3 and R4 value is nothing but the, it's also the pressure ratio in the expansion side. R3 is the value of P3 by P4. This is the P3 or P2 value. So I mean in this line, P2 is equals to P3. So we can simply comment that the R3 is nothing but P3 by P4. That means this line, this is a constant pressure line. The R3 is the ratio between P3 by P4, and R4 is the pressure ratio between the P5 and P6. R4 is the ratio, the pressure ratio between P5 and P6. Since this is a constant pressure line, so again we can write that once again, that is P4 is equals to P5, and for this line we can write P1 is equals to P6. Okay, so again I am telling you that R3 is the ratio between P3 by P4. R3 is the ratio between P3 by P4, and R4 is the ratio between P4 by P6. Okay, so the C is already you know that C is uh, R to the power gamma minus 1 by gamma is equals to T2 by T1, and C3 is R3 to the power gamma minus 1 by gamma is equals to T3 by T4, and C4 is R4 to the power gamma minus 1 by gamma is equals to T5 by T6. So C is equals to C3 into C4, the same as this relation, that is R equals to T3 into T4 R4, R equals to R3 into R4, same as C equals to C3 into C4. So in this figure we can again write the reheat temperature, that means this 3 and 5, this reheat temperature, that is this 3 and 5, this temperature is the constant temperature. I mean these two temperatures are the equal. The first combustion chamber temperature, and the second reheat combustion chamber temperature, the maximum temperature, these two temperatures are the same. Okay, so the specific work output becomes, that is Wn by Cp into T1 is equals to 2 into T equals to T by C3 minus T by C4 minus C plus 1. To gain the maximum specific work output, we have to assume that is C equals to root over C into is equals to C4. That means the it's a GPC series. We can assume that is C3 is equals to C4 is equals to root over C. Okay, so to obtain the maximum specific output stage, the pressure ratio must be same and equal to the square root of the overall pressure ratio for two-stage expansion. So the maximum specific work output becomes W max by CPT1, that is equals to 2 into T into 1 minus 1 by root C minus C minus 1. So the maximum efficiency becomes 2 into T 1 minus 1 by root C minus C minus 1 by 2 into T minus C minus T by root C. Okay, the efficiency less due to the small temperature operating range. Okay, now the reheat and heat exchange cycle, this is the combination of both two cycles. Okay, so to the increase the specific power output in the reheat cycle in the expense of the efficiency, and it can be overcome by adding a heat exchanger to the reheat cycle. So let's see the arrangement and the working principle. So this one is the compressor, this is the turbine 1, and this one is the turbine 2. Okay, these two are the combustion chamber. This is the first one, this is the reheat combustion chamber, and this one is the heat exchanger. The process is like, first the air is entering to the combustion chamber, then it's compressed, that is 1 to 2, the adiabatic compression process 1 to 2, the constant entropy process, and temperature is slightly increased here. Then the air flows to the heat exchanger. Here it gains some heat from the uh, outlet exhaust, the product, or from the flue gas. Then the air, okay, one thing, so that 2 to 7, this is 2 to 7, it increased some heat. Okay, this is the 2 to 7 process. This is a constant pressure process. 2 to 7 increased or gained some heat from the combustion product. Then after the point 7, it enters to the combustion chamber. Here it mixes with the fuel and combustion takes place, that is 7 to 3. This is 7 to 3 process, the constant pressure process. This is 7 to 3 process, 7 to 3. Okay. After that combustion chamber, that combustion product then flows through the turbine. This is the expansion process, 3 to 4. Adiabatic expansion process, this is 3. This point is 4. This is a constant entropy process, 3 to 4. Adiabatic expansion process. After flowing through the turbine 1, then again it enters to the reheat combustion chamber. In the reheat combustion chamber, again it's mixed with some fuel and combustion takes place. That is 4 to 5. That is 4 to 5. Again the temperature increase 4 to 5. Then again it flows to the turbine, that is 5 to 6. 5 to 6. This is 5 to 6. This is the second stage of expansion. Okay. And 6 to 8. 6 to 8. Then after leaving the system, it gives its heat to the air, the compressed air in the heat exchanger. It exchanges heat with the compressed air, and it loses some heat, and the compressed air gain heats. Okay, so 6 to 8 is the heat exchanger process. This is 6 to 8, and 8 to 1 is the exhaust. So 81, 8 to 1, 8 to 1 is the exhaust. Okay. So the heat addition, that is first first heat addition is 7 to 3. The first in the first combustion chamber, 7 to 3, Q7 3, and second heat addition is 4 to 5, that is Q4 to 5. So that is equals to Cp into T3 minus T7 plus Cp into T5 minus T4. Okay. Turbine work, it has in this system it has two turbine, that this is turbine 1, this one is turbine 2. So W 3 to 4, 3 to 4, and plus W 5 to 6, this is the 5 to 6. So that is equals to Cp T3 minus T4 plus Cp T5 minus T6. Okay, this is the turbine work. Now the maximum specific work output is the same as the reheat cycle, that is W max by CPT1, that is equals to 2 into T into 1 minus 1 by root C minus C minus 1. Okay, so the maximum efficiency will change due to the heat exchanger. So the maximum efficiency becomes this is the uh, work output, the maximum work output. This is not the maximum specific work output. Okay, since the CP and T1 is multiplied here, it's the maximum work output, not the maximum specific work output. Okay, this is the maximum work output. So that is Cp into T1 into 2 into T, 1 minus 1 by root C minus C minus 1 by the heat input, that is Cp into T3 minus T7 plus Cp into T5 minus T4. So that becomes, that is since the Cp T7 equals to T4 and T5 is equals to T3. Okay, now we are just multiplying, dividing this temperature. So here the CP cancelling out. So the T3 by T1, now we are going to divide this denominator by this T1. Okay, we are going to divide this denominator by T1, this T1. So that becomes T3 by T1 minus T7 by T1 plus T5 by T1 minus T4 by T1. Okay, so this is the expression. So the since the T7 equals to T4 and T5 equals to T3, so the maximum efficiency, that becomes 1 minus C minus 1 by 2T minus 2T by root C. Okay, so this is the expression for maximum efficiency. So let's do a simple numerical. It says that uh, compute the indicated mean effective pressure and efficiency of a Joule cycle if the temperature at the end of combustion is 2000 Kelvin and the temperature and pressure before the compression is 350 Kelvin and 1 bar. The pressure ratio is 1.3. Assume Cp equals to 1.005 kilojoule per kg Kelvin. So since it's a simple Breton cycle problem, the PV diagram is shown here. That is 1, 2, 3, 4. 1 to 2 is the adiabatic compression process. 2 to 3 is the combustion process, constant pressure combustion process. 3 to 4 is the adiabatic expansion process through turbine, and 4 to 1 is the exhaust, constant pressure. So let's consider. We are considering that that I have telling you that the T1 is equals to the T2 is equals to for the isentropic compression process, that is 1 to 2. T2 is equals to T1 into P2 by P1, and T1 is the inlet temperature, P2 by P1 is the pressure ratio. P2 by P1 is the pressure ratio. So by substituting all these values and gamma equals to 1.4, we are assuming that gamma for air, that is 1.4. This is the gamma. This is gamma minus 1 by gamma. Gamma minus 1 by gamma. Gamma is 1.4. So by substituting all these values, we get T2 equals to 377.27 Kelvin. Now again, considering the process 3 to 4, this is also the adiabatic process 3 to 4 or isentropic process, reversible adiabatic process or isentropic process. So T4 becomes T3 into T4 by P4 by P3. T4 is equals to T3 into P4 by P3. Here P3 and P2 is same and P4 and P1 is same. So P4 by P3 is becomes 1 by pressure ratio, that is 1 by 1.3, and T3 is the 2000 Kelvin. It's given here. That is at the end of combustion is 2000 Kelvin, the maximum temperature. So the T4 becomes 1855.24 Kelvin. Okay. Now the work done in the compression process, that is the WC, that is Cp into T2 minus T1. So that is 27.40 kilojoule per kg, and the work done in turbine process, that is Cp into T3 minus T4, that is 145.30 kilojoule per kg. So the net work done, that is Wn, that is Wt minus Wc, that is 117.90 kilojoule per kg. Now the various state points, the volume at various state points. First one, the V1, that is we can write V1 is equals to RT1 by P1. So R value is 0.287 into 10 to the power 3 joule per kg Kelvin into 350 by 1 into 10 to the power 5, because P1 is the 1 bar into 10 to the power 5, so that becomes 1.0045 meter cube per kg. Similarly, the V2 is R into T2 by P3, R into T2 by P3, and V3 is R into T3 by P3, and V4 is R into T4 by P4. So the V2 is value is this, that is 0.833 meter cube per kg. V3 is 4.415 meter cube per kg, and V4 5.325 meter cube per kg. Okay. So the indicated mean effective pressure is net work done by the change in volume. So the net work done, that is Wn, and the change in volume, that is V4 minus V2, is the change in volume. Okay, V4 minus V2. So the mean effective pressure is becomes 0.2625 bar. The heat input, that is Q, that is Cp into T3 minus T2. Cp into T3 minus T2. So that becomes 1630.84 kilojoule per kg. Now the efficiency, so the efficiency becomes net work done by Q. So that is 7.23%. This is very low. Okay, since the pressure ratio is quite small. Okay, the pressure ratio is quite small. In spite of the higher peak temperature, the efficiency is very low. This is the example that define that the efficiency of a simple cycle depends mainly on the temperature ratio and not on the peak temperature. Okay, that means the efficiency of a simple cycle is depends on the pressure ratio, not on the peak temperature. So in this lecture we have learned the we have derived actually the efficiency of reheat cycle, heat exchange cycle, and reheat and heat exchange cycle. In the next lecture, we will derive the efficiency of some other cycles, that is intercooled cycle and the combination of intercooled and heat exchange and reheat cycle, and we will do some other numerical. Thank you.